Hi, I'm Benny, and I've dedicated my life to understanding the universe, with the hope that one day I'll get the chance to hop on a rocket and see it for myself. Growing up, I was always looking up, not just at the stars, but at the endless questions they sparked. I'd spend hours wondering what was out there, how it all worked, and if I'd ever get the chance to see it for myself. This is Space Bites, where I take the overwhelming, mind bending world of space and break it down into small, easy to digest pieces. Think of it like snacking on the cosmos, quick, simple, and deliciously full of wonder, so anyone can understand and enjoy it no matter their background. Why? Because every atom in your body was forged in the heart of a star. The carbon in your DNA, the oxygen you breathe, the calcium in your bones, all of it began in stellar furnaces, which means, quite literally, the universe is in you. You are the product of cosmic alchemy billions of years in the making. The same processes that built galaxies also built you, linking your existence to the cosmos itself. Hello, everyone, and welcome back to another episode of Space Bites with Benny. It's me, Benny, your favorite nerd. There's a strange thing about physics, and it's that the deeper you go, the less solid the world becomes. So a table feels solid, a wall feels solid, your body feels solid. But if you zoom in enough, that solidity sort of starts to disappear, right? So matter becomes atoms, atoms become nuclei and protons become nuclei become protons and neutrons, and those protons and neutrons become quarks. And holding all of this together are fields. So electric fields, magnetic fields, quantum fields, and gravitational fields. And they're kind of the invisible architecture behind what is visible behind our reality. And I originally came into physics through astrophysics and cosmology. So it's like the science of the largest things that you can imagine, like galaxies and black holes and the cosmic microwave background and the going back in time all the way to the early universe and even the structure of space-time itself. But over time, my interests kind of started to move inward. So, not really away from the universe, but more towards the machines and the physical systems that let us recreate pieces of the universe here on Earth. So, I became increasingly interested in particle physics, high energy plasma physics, and particle accelerators. So, no longer just observing the universe from far away, but also building the tools that let us probe matter and energy and fields directly. And it kind of feels like going from reading a weather report to learning how to seed clouds. So I remember asking some of the audience what they'd like to know about particle physics and accelerators and high energy beams and all that other stuff. And, really before going into anything more complicated, we have to start with the basics, the foundation. So we start with electricity and magnetism. And so we start with Maxwell. Okay, so to picture electric fields, um, just kind of use your imagination for a second and think of it like this. If you're standing at the edge of a lake one morning and you drop a stone into the water, you'll see ripples spread out in every direction. And it's not because something is physically touching the shore, but because the surface of the water has been disturbed. So something invisible has propagated through the medium here being the water, the lake. But if you take away the water and you take away the ripples and you only keep this idea that a single object can change the space around it, and that other objects entering that space will also be able to feel it, then you have the idea of an electric field. When a charged particle sits in space, it doesn't just sit there it reshapes the space around it. It creates a distortion in the space, one that is structured, and you can kind of imagine it as a set of invisible lines of influence that extend outwards from the object and into every direction. And that distortion, that that change in the space is the electric field. And so if you bring a second charged particle closer to the first one, even if they don't touch, the second charged particle is able to read the electric field. It feels the distortion and it responds. How does it respond? Well, if the charges are opposite, so if one's positive and one's negative, then they're pulled toward each other. But if they're the same, they get pushed apart. And so the key insight here is that the force between two charges is not it's not transmitted directly. It's not like two hands grabbing at each other. It is more like it's transmitted through the field. The field is the intermediary between these two particles. It's the messenger. And so think of it this way. When you're standing outside and the sun warms your face, the sun isn't touching you. Energy is traveling through the field. The electric field and the magnetic field are the medium through which energy moves. And so that's literally what light is. And the scale of what electric fields can govern is quite staggering. And I think this is why I decided to start the episode talking about electric fields. Chemical bonds are electric. The attraction between protons in a nucleus and electrons in orbit is electric. The signals in your brain, the signals your neurons send are electric. Every time you lift up a coffee cup, the electrons in your fingertips repel the electrons in the ceramic of the coffee cup. They're what stop your hand from passing straight through the table. You have never actually touched anything in the direct sense, in the way that we imagine touching, but rather what you have felt your entire life are electric fields. So, electricity at rest creates an electric field. But what happens when electricity starts to move? And this is when something new comes up, and that's magnetic fields. And I think this kind of surprises people at first because magnetism and electricity might seem really different. A compass needle and a lightning bolt, like they feel like completely unrelated things, but they're not really separate in the way that you think. Magnetism is what electricity looks like when charges are in motion. So, for example, run current through a wire and a magnetic field curls around it like invisible rings. Set an electron spinning and it generates a magnetic dipole, a tiny bar magnet. The Earth's magnetic field is generated by churning electrically conducting fluid deep inside its iron core, and it's millions of amperes of current moving in slow, enormous loops. And so here's the strange part about magnetic fields, and it is it really matters for what comes later. Magnetic fields do not push charges forwards or backwards. They push them sideways. So if you have a charged particle moving in a straight line and it enters a magnetic field, the field does not speed it up or slow it down. It deflects it, it kicks it, it curves its path. Depending on the geometry, you can bend that path into an arc or even into a perfect circle. So imagine a river with a very powerful current running perpendicular, so at 90 degrees to where you want to go. If you enter the river and instead of being pushed downstream, the current bends you sideways. You travel in a curve. If the field is arranged just right, you curve all the way around and come back to where you started. And that is exactly what magnetic fields do to charged particles in an accelerator ring. So already, before we have even talked about quantum mechanics or plasma or colliders, we have the two fundamental tools of accelerator physics. You can think of electric fields as the engine and magnetic fields as the steering wheel. And everything else is just the details behind all of this. They are remarkable, they are complex, they are beautiful details, but they are built from those two ideas. I also enjoy including little history or like historical facts. So for this episode, we'll go back to a moment where that changed everything. And so in the 1860s, James Clerk Maxwell sat down with all the known laws of electricity and magnetism. So those included the work of Faraday, Ampere, Gauss, and others. And he did something that at first looked like a very small mathematical correction. So Maxwell noticed an inconsistency in the equations. So he added a term, a small modification to account for the fact that a changing electric field should, in principle, generate a magnetic field, even without a physical current flowing. It turned out to be one of the most consequential additions in the history of science. So, with that fix in place, Maxwell's four equations described electricity and magnetism as a unified system. And when he solved them together, when he solved these four equations, something fell out of the mathematics that no one had expected, which is a wave. A self-sustaining wave of oscillating electric and magnetic fields, each generating the other, propagating through empty space. And this is in my opinion, one of the most beautiful ideas in physics. So let's unpack this. What does it mean? What does oscillating mean here? So if you have an electric field that points upward, then grows stronger, then weaker, then flips and points downwards, then grows stronger again in that direction, then it flips back, that is an oscillating electric field. It's not static. It's not moving. It's cycling like a pendulum, like a grandfather clock that swings back and forth. Except what it is swinging here is the direction and strength of the field itself. And here's the key piece, which comes directly from Maxwell's equations. A changing magnetic field creates an electric field, and a changing electric field creates a magnetic field. Not a static field, a changing one. And this is the crucial word. If the magnetic field just sits there, nothing new happens. But if it is changing, growing or shrinking or flipping, then it generates an electric field in the space around it, and vice versa. So picture this sequence of events. You disturb the electromagnetic field somewhere. Maybe a charged particle accelerates, and that creates a changing electric field. That changing electric field generates a magnetic field. But that magnetic field itself is changing. It had to build up from nothing, right? So it generates a new electric field, which is also changing, which generates a new magnetic field. And this can just go on. And each field is constantly knitting the other one back into existence. And think about where this is happening. The electric field that gets generated is not in the same place as the magnetic field that caused it. It's slightly ahead of it, in the direction the disturbance is traveling. So the process does not just oscillate in place. Again, this thing, it's not static. It's not moving. It propagates. It moves. It's traveling. Each cycle of the mutual generation of fields pushes the disturbance forward through space. And this is what I meant by self-sustaining. The wave does not need a medium to carry it. It does not need air or water or any material. The electric and magnetic fields are carrying each other. They're the medium and the disturbance at the same time. So here's a metaphor, since we love metaphors so much. Imagine two people standing in front of each other and they're passing a ball back and forth while walking forward. So neither person can move without the other one throwing the ball to them. The ball going from person A to person B is what moves A forwards. The ball returning from B to A is what moves B forward. And so they're sustaining each other, they're keeping each other going. And the whole system advances through space as a result. In the electromagnetic wave, the electric field throws to the magnetic field, which throws back to the electric field, and the whole structure moves forward at the speed of light. And so what does empty space mean here, and why does that matter? Well, that's because before Maxwell, waves were understood to need a medium. Kind of like how sound waves need air. Ocean waves need water. Even physicists assume that light must need something. And they called that the luminiferous ether. some invisible substance filling all of space that light waves rippled through. And so Maxwell's equations said, no medium is required. The fields themselves are enough. They sustain each other. A changing electric field does not need anything around it to generate a magnetic field. It does it to the space itself, the fabric of the field that permeates everything. And I guess it kind of makes sense that this would be unsettling at the time, and meant that space was not just an empty container that they thought it was. It was something that could support fields, it could carry energy, and it could propagate disturbances without really being made of anything in the ordinary sense that we would say something is made of something. So here's the full picture. An electromagnetic wave, basically light, is two fields, electric and magnetic. And when they're oriented perpendicular at 90 degrees to each other and perpendicular to the direction of travel, they're oscillating in lockstep, each one continuously generating the other. The whole structure moves forward through space at roughly 300,000 kilometers per second. That is the speed of light. Every photon, every radio wave, X-ray, all of it is the same self-sustaining mutual generation. And Maxwell found this in the math before anyone could verify it experimentally. He saw the wave solution sitting inside his own four equations and recognized it from the speed it predicted, that it had to be light. The universe had hidden the nature of light inside the laws of electricity and magnetism. And it took a man like Maxwell tidying up inconsistencies in some equations to be able to find it. So moving forward in time, we come to the end of the 19th century, and now light is understood as a wave. Maxwell had proved it, experiments confirmed it, and physics seemed settled. Then the 20th century arrived, and light started to behave strangely. When physicists shone a light on metal surfaces, they found that the light could knock electrons loose, but only if the frequency was high enough. So at a high enough frequency, the orbiting inside of an atom could be knocked loose. And turn up the intensity all you wanted. If the frequency was too low, nothing happened. But increase the frequency even slightly above a threshold, a certain value, and the electrons started to fly off. And we called this the photoelectric effect. And it did not make sense for a wave, because waves are continuous. If light is a wave, more intensity should always mean more energy. But this is not what the experiments were showing. And so Einstein's explanation in 1905, almost 100 years after Maxwell, was radical. Light does not just behave like a wave. It also comes in small, what we call discrete packets or quanta. Each quantum, the plural of quanta, each quantum carries a fixed amount of energy that is determined by its frequency. Okay? And those quanta, those little packets of something, are what we now call photons. A photon is the smallest unit of light. It's not a particle in the old-fashioned, billiard ball sense, and it is not purely a wave either. It is something the classical world has no good category for. It is a quantum of the electromagnetic field. It is a packet, a small bite, a little breadcrumb. If the electromagnetic field is the whole loaf of bread, then the photon is a little crumb of that. It is a quantum of the electromagnetic field. And so this is where physics makes a leap that still feels pretty big when you really sit with it. In quantum field theory, every particle is a quantum of some underlying field. An electron is not a tiny marble with a fixed location and a fixed path. It is an excitation of the electron field, a ripple, a vibration. It is a localized disturbance in a field that permeates all of space. So the best analogy for this that I can think of is a guitar string. The string itself is the field. It runs continuously from one end to the other. When you pluck the string, it vibrates at a specific frequency. Those vibrations, those notes, are the particles. Different strings are different fields. Different notes are on the same string are different energy states of the same particle type. When particles are created in a collision, it is not as if they were hiding in the proton, waiting to be found. No, a field was disturbed, and the disturbance organized itself into something we detect as a particle. So the universe is not just a collection of things, it is a collection of patterns. I think that's a good 20 minutes on quantum fields, electric fields, and magnetic fields. Let's go back to where we started. The world feels solid, and it feels it's made of things. Objects with edges, with weight, with presence. You knock on a table, and it knocks back. Matter feels like the most basic fact of reality. And we have spent this episode pulling at that intuition, and it really has not held up. What we found underneath is not things, it's fields. Fields. Imagine just fields running through everything that you see around you. Because space is not empty, it never was. It's threaded through with electric and magnetic fields, structures that extend everywhere from just different points around us. And they respond to the presence of charge that can carry energy and information across the void between a star and your retina without touching anything in between. And when Maxwell wrote down the equations that unified those two fields, something fell out of the mathematics, a wave, a self-sustaining structure of oscillating electric and magnetic fields, each one generating the other, propagating through space at a fixed speed. And that speed matched the speed of light. And he wasn't really looking for light, he was just doing some adjusting, some bookkeeping, if you will. And he found that light is not a thing that moves through the universe, it is a motion of the universe itself, a ripple in the field structure that underlies everything. Then the 20th century arrived, and even that picture cracked open, because light, which Maxwell had shown was a continuous wave, turned out to also behave like a particle, and the photoelectric effect forced that conclusion. Einstein named those particles photons, and once you have a particle of light, once you have a quantum of the electromagnetic field, then a deeper question immediately surfaces. If light is a quantum field, then what about electrons? What are protons, and what is matter? Quantum field theory gives us that answer, and it is the strangest, most beautiful idea in all of physics, or at least one of them. The idea is that everything is a field, not just light, not just electromagnetic radiation, but every particle you have ever heard of, electrons, quarks, neutrinos, even the Higgs boson, is an excitation of some underlying field, a localized vibration, a place where a field has been disturbed in a way that behaves like a particle. There's an electron field permeating all of space right now. When it vibrates in the right way, we detect what we call an electron. There is a quark field, a Higgs field. The universe is not a collection of objects moving through empty space. It is a collection of fields. And objects are what those fields look like when they're disturbed. And so this is the foundation, and it really matters for everything that comes next. Because if particles are excitations of fields, and fields respond to electric and magnetic forces, then the way to study particles at the deepest level is to use fields to manipulate them, to accelerate them, and to steer them, to smash them together hard enough that the energy of the collision disturbs the underlying fields and shakes new particles into existence. And that is what a particle accelerator does. It is a machine for interrogating fields. And at its core, it runs on the same physics that Maxwell wrote down in the 1860s. The same oscillating electric fields, the same magnetic steering, the same wave structure that carries energy through space. So I think that was a good first 20 minutes on different fields and how this all plays into particle accelerators. Thanks for listening. Until next time. So thank you for listening, and